I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. I am Amraraj Sawant, Assistant Professor from Department of Mechanical Engineering. So today is lecture number 4. In this lecture we are going to see the Fourier law of conduction. So in last lecture we have seen that modes of heat transfer. So basically there are 3 modes of heat transfer: conduction, convection and radiation. So for conduction heat transfer, we are going to see how the Fourier law is governing for this conduction heat transfer and how this law is applicable to the various processes. So this law, Fourier law, is named after J.B.J. Fourier. So he was a scientist, and this law is governed for conduction heat transfer process. So it describes how the thermal energy is transmitted through the solid medium. Once again I will repeat this. It describes how the thermal energy is transmitted through the solid medium due to the temperature gradient. As we have seen in last lecture, the heat transfer only occurs when the temperature gradient or the temperature difference will be there. So this law is applicable only when there is a solid metal or solid state where the heat transfer takes place. Okay, so this law will be the fundamental, or it is used as a fundamental to the thermal insulation or heat exchanger and electronic devices. So what is the Fourier law and the statement of it? So Fourier law states that the rate of heat transfer, so rate of heat transfer means the heat transfer per unit time. Okay, so the rate of heat transfer through the material is proportional to the negative gradient of temperature. In last lectures I have taught you that what is the temperature gradient. The temperature gradient is a temperature difference with respect to some distance. Okay, so and that area perpendicular to the gradient. So Fourier law states that the rate of heat transfer is always going to be equal when it is having some negative gradient of temperature and the perpendicular area where the heat transfer takes place. So its equation, mathematical equation, is Q is equal to minus K dt by dx. Here Q is a heat flux. Heat flux means heat transfer per unit area. So heat transfer rate is directly proportional to the negative gradient of this, okay, by the Fourier law. So we are going to see how it is actually takes place with this example or with this image illustrated here. So let's consider this as a block, okay, of thickness L, and left side of this block is having hot or high temperature and right side of this block is having low temperature or cold side. Okay, so as I taught you earlier lectures that the heat is always transferred from higher temperature to the lower temperature, or in other words, the any energy can be transferred from higher energy level to the lower energy level by virtue of second law of thermodynamics. So basically here the heat transfer is going to take place in this direction, okay, and it is linear, and how it is linear that we have seen in last lectures. So Fourier law for heat conduction states that this transfer of heat is equal to negative gradient or negative of temperature gradient. What is meant by temperature gradient? Difference between this temperature, let's say T2 minus T1, divided by what is the distance here, which is L, which is thickness of this block, and the area where this area, let's say this in 3-dimensional, so this area will be calculated, okay, or will be taken into account for calculating the total heat transfer. Okay, so the heat transfer rate is directly proportional to the negative gradient of temperature. So heat transfer, whatever the heat is going to transfer here from this temperature, higher temperature to lower temperature, it is directly proportional to this gradient of temperature. Okay, and what is mean by gradient of temperature or temperature gradient? That is the difference between the temperature upon the length or upon the distance. Okay, so heat flows from high side or higher to lower temperature. Higher side or hot side to the cold side, heat, as I stated in according to the second law of thermodynamics, heat is always flow from high temperature to lower temperature. Okay, so explanation of terms Q, likewise I said before, Q is a heat flux. Heat flux, which is Q divided by area. Q here is a heat transfer, and area, which is I have just explained here, area, if we think this block in 3-dimensional, the area which is having the heat transfer. Okay, so Q here is a heat flux and its unit is watt per meter square. K is a property of that material, which is thermal conductivity. Its unit is watt per meter Kelvin. And what is the thermal conductivity, how it is going to change, and how its importance in the heat transfer, that we will going to see in further lecture. So as I stated, temperature gradient is equal to dt by dx, which is difference in a temperature upon total distance within that temperature difference. So here one important thing is there. The negative sign shows that heat is always flow from hot side to the cold side. This is the one important aspects of Fourier law. Why this negative sign is there in this law? Because let's take this example. In this example, if we think that heat transfer will be taken place from this side to this side, okay, like hot side to cold side, okay, but while calculating the temperature gradient, calculating this temperature gradient, we are taking this temperature and this temperature. Okay, so temperature gradient is nothing but the difference in a temperature with respect to their distance. Okay, with respect to distance traveled by that heat. So T2 minus T1, if in this case, will always be negative. Okay, let's say this temperature is 100 degrees Celsius and this temperature is 40 degrees Celsius. Okay, so 40 minus 100, but obviously it is minus 60. Okay, and if we think in the direction like that, so our temperature gradient value becomes negative. So without negative sign, you would incorrectly get a negative heat flux. Okay, so in this you will get negative heat flux, and suggesting that the heat is flowing from cold side to the hot side. Okay, and as we know, as per the second law of thermodynamics, heat is always flowing from higher side to lower side, or higher temperature to lower temperature. If we don't take a here negative sign, then it implicates that the heat is flowing from cold side to hot side, and that will not going to happen. So that's why we have taken, or Fourier have taken, this negative sign in this equation. Okay, this is one important aspect of Fourier law. So next term is what is mean by the steady and transient conduction. As we have seen this steady and transient conduction in before the modes of heat transfer, where the conduction has two types: conduction with a steady state and conduction with a transient state. As I have taught you earlier, the steady state means temperature remains constant with the time. That is mean by where the temperature, in previous example, let's say here one side is 100 degrees Celsius and another side is 40 degrees Celsius. So this temperature with the time, it will not going to change. Okay, is a steady state. That is what illustrated in this figure. So let's consider this figure. For steady state, first of all, for steady state, the temperature remains constant with the time. Okay, so let's take this example. Let's say at a 2 p.m. you have a cylindrical block, and that cylindrical block is experiencing the heat transfer from 25 degrees Celsius to 15 degrees Celsius. and after some 4 hours at 6 p.m. same temperature difference will be there, then the process from 2 p.m. to 6 p.m. the heat transfer will be called as steady state. Okay, and in transient vice versa. In transient, after this, let's say at a 2 p.m. this cylindrical block is experiencing a heat transfer from 25 degrees Celsius to 15 degrees Celsius, but after 4 hours at 6 p.m. this temperature will going to be decrease due to some external things like atmospheric temperature will be decreases, or some atmospheric air will have some more velocity, that's why, or some external effects are there, so that's why this temperature will going to decrease in actual practices. Okay, but so for that this case is termed as transient or unsteady condition, which is actually there in our real practices, but for easiness of understanding the engineering problems, we have considered sometime the cases to be steady state condition. Okay, so what are the applications of Fourier law? As we have seen that the Fourier law states that the heat transfer is equal to negative of temperature gradient. It is directly proportional to the negative of temperature gradient, and it is directly proportional to the thermal conductivity of material. So what is the application of this Fourier law? So in this example, in this previous example illustrated here, okay, so in this example we have seen that the heat transfer is taken place. Let's say this is a solid block, and the heat transfer is going to take place from this hot side to the cold side. Okay, but in actual practices, how this law is applicable to our engineering or day-to-day life? So here we can see that the heat exchanger design, building insulation design, electronics cooling, engine heat flow analysis, biomedical devices, geothermal studies, all of these were come to basic thing that any material having certain length or certain thickness and having certain area will experience a conduction heat transfer. And the conduction heat transfer, where it takes place? When there is a solid state is there, because of that solid state material will have atoms and molecules in there, and that atoms and molecules will vibrate with their central position and some free electrons that will cause the heat transfer in a solid state. Okay, and so this solid state we will experience in everywhere. Okay, in engine, the engine block or the piston having in a solid state, which is made up of a metal, which is a solid state, and that in that engine block, the heat transfer from piston to the cylinder block, or for outside that, it will take place by the conduction. Also in this building material, how the building is constructed? The building is constructed with some walls and columns, and the walls and columns are made up of solid material, and that solid material having some molecules and atom that will also vibrate with their central position, and due to which the conduction heat transfer takes place. That's why Fourier law to calculate how much heat transfer will take place according to different types of materials in a solid state. Okay, so what is the limitations and assumptions of this Fourier law? So we assume that the material is a homogeneous. What is mean by homogeneous material? Homogeneous material means that the property of that metal, or density or porosity or anything is everywhere same. Okay, everywhere same in all direction, in x direction, in y direction, in z direction, everywhere the material properties are same to the respective material. Let's say you are considering a steel block, then the steel throughout the block will be same. So that will be called as a homogeneous material. And why we assume as in here the homogeneous material? Because in non-homogeneous material, let's say in a composite material, the thermal conductivity, that is a material property, will going to change with the distance. Okay, and so in Fourier law, just now we can't predict the heat transfer with a non-homogeneous material, and for predicting the heat transfer for non-homogeneous material we have to take some derivations and considerations of Fourier's law, but that will be right now not aspects of this course. But so that's why the homogeneous material we have considered, or we have assumed that every material is a homogeneous material to calculate heat transfer with this Fourier law. Okay, there will be the small temperature gradient. So while considering, likewise I have just before we have seen that building insulations, okay, or electronic device, or any you can take any example. So in this example you have seen that the temperature gradient will be not more. Okay, for temperature gradient will be more in which cases? When there is a length or distance also more. Okay, it is a common practices. If we insulate some let's say some building, okay, and the building having walls, how much generally how much thickness of that wall will be there? Some 10 inches or maybe maximum up to 12 inches. Okay, after that if you put 1 meter of wall, then it is not economical. So that's why the Fourier law is applicable, or we assume the temperature gradient will be smaller. Okay, constant thermal conductivity, as I have just said in first point, that homogeneous material should be there, or we assume that the material is homogeneous. That's why, because if we take two materials in one system, then the material conductivity will going to be changed, and for calculating the heat transfer there will be some derivation, and there will be difficulty with a simple Fourier law equation. And totally 750, and in total it is calculated as 750 Kelvin per meter, which is temperature gradient. And as our Fourier law states that heat flux, so here we have to calculate the heat flux according to the Fourier law of heat conduction. The heat flux is equal to minus K multiplied by temperature gradient, which is dt by dx. Just we have calculated the dt by dx is equal to 750 Kelvin per meter. So just we have to multiply these things. So thermal conductivity of concrete is 1.5 multiplied by 750, which is temperature gradient, in total minus 1125 watt per meter square is a heat flux. Heat flux means heat transfer. This is equal to heat transfer per unit area. So this we have to calculate by, and this we have just calculated by using the Fourier law. So the negative sign indicates, as I have stated earlier, the negative sign indicates that the heat is flowing from hot side to the cold side. If we don't take this negative sign, then 100 minus 25, just we have calculated, and this term will get positive. And let's say in another scenario, if the temperature will be reverse, let's say is 25 to 100. Here if the temperature is 25, okay, and here the temperature is 100, okay, then this if in Fourier law this negative sign is not there, then the heat flux is going to be negative. That implicates that the heat is flowing from cold side to the hot side, which is not possible due to the second law of thermodynamics. So thank you very much. So with this lecture I will conclude the Fourier law of heat conduction. You will have to attend the assignment regarding this lecture. It will consist of 20 multiple choice question, and you will find the assignment in the description box. And feel free to ask me anything regarding this lecture in discussion forum box, and also the notes of this lecture, also the ebook of this total entire course will be available to you in the description box later on. Thank you very much.